Hey there, it's Shannon Myers. I hope you're having a fabulous day today. And we will be exploring the third part of direct proof and counterexample today. And this deals with divisibility. So let's get started. The notion of divisibility is the central concept of a subject in advanced math called number theory. And number theory deals with the study of properties of integers. So our first definition gives us if n and d are integers and d is not equal to 0, then n is divisible by d if and only if n equals d times some integer. So just like some of the other things that we've been looking at, an even number in math is something that can be written as 2 times some integer. An odd number in math is something that can be written as 2 times some integer plus 1. This is your setup for a lot of these divisibility proofs. All right, so there's different ways we can look at this. Instead of saying n divisible by d, we can say that n is a multiple of d, or d is a factor of n, or d is a divisor of n, or d divides n. And there's actually special notation for that. So this notation here, this d with the straight line and then the n, means d divides n. Symbolically, if n and d are integers and d is not equal to 0, d divides n if and only if there exists an integer k such that n is equal to d times this k. All right? And remember, k could be any integer that makes this statement true. So let's just look at some basic stuff about divisibility first. Is 54 divisible by 3? Well, there's some cool tricks here. If you add the digits in a number and that number is divisible by 3, then the original number is divisible by 3. So 5 plus 4 is 9. Well, 3 divides 9, so 3 will definitely divide 54. So let's write it a little differently. Let's go ahead and say, okay, well, yes. And why are we going to say yes? Because we can write 54, which is the n in this case, right, is equal to 3, which is the d from the definition. And 3 times what is equal to 54? Beautiful. 18. Okay? All right. Does 4 divide 76? Well, yes, there is a trick for 4s. If 4 divides the last 2 digits in a number, so in the tens and ones place, then it will divide the original number. So 4 does indeed divide 76. So that means 4 will divide 176. So, yes, 176 equals, beautiful, 4 times, and I think it's 44. Good so far? Awesome. All right, is 12 a multiple of 24? Be careful. A multiple of 24, the smallest multiple of 24 is what? Beautiful, 24. So no, 12 is not a multiple of 24. All right, what about this next one? Is 6 a factor of negative 6? Sure, right? So again, we'll say, give our yes, and then we'll say negative 6 is our n this time, and that's equal to 6 times 1. Oops, sorry. 6 times negative 1. Cool, cool? All right. So now let's look at the first theorem of this section. For all integers a and b, if a and b are positive, and if a divides b, then a must be less than or equal to b. So again, in Appendix A, if you recall, there were all these things are assumptions, meaning we can assume that they are true, have been proven. So we will be taking a look here for our one of our tools to give our statements credence, all right, at least one of them. So let's just take a look here and let's get the startup done. So what do we do first? Perfect. You write the word proof. All right. See? Already earned a point, or at least a half a point. Okay, so what are we going to need? We have these integers a and b. We know that they're positive integers, and we also know that a divides b, right? That's all given. So, meaning that that's all in our premise. So, let's identify these things. Suppose a and b, remember that positive integers is the z with the plus sign, or you can just write positive integers. So a and b are positive integers, and a divides b. Good so far? Well, now let's look at this a divides b part. Since a divides b, there exists some k that belongs to the integer. So it can be any arbitrary integer. Such that, so remember, this backwards epsilon is such that b equals a times k. Cool so far? And that, what is that by? I mean, why can I say that? It's by definition, right? Specifically definition of divisibility, but we can just write definition here. Good so far? All right. Since a and b are both positive, what do you think? Well, wouldn't it follow that k is positive? So it probably makes sense, right? But let's look at these theorems, right, and see if there's anything that we know. Here. Good. If you look at Theorem 25, right? Theorem 25. If you have a product that's greater than 0, then both A and B have to be positive or both have to be negative, right? Well, it's a little bit tricky here because we're not technically going to be using A and B, right? What are we going to be using? Awesome. We're going to be using A and K. B is positive. A is positive. So in this theorem 25, that's reading AB greater than 0, we're looking at it as AK is greater than 0 because A times K equals B and B is positive, right? So we'll write that proof by saying theorem 25 Alrighty, so thus we have one is less than or equal to K. Why is it I can say that? Well, what did we decide about K? We decided that K was positive, didn't we? Right? K is positive. And K is what else? K belongs to the integers, right? So that is why we can say that, because 1 is the smallest positive integer, right? So we can say that's because K belongs to the positive integers. Cool so far? All right. So next up, well, what could we do here? We know that A is non-zero, so we can go ahead and multiply both sides by A. Well, why would I be doing that? Perfect, because we want to get B and A in this inequality. And B is equal to what? Perfect, A times K. So A times 1 is just A, and we have A is less than or equal to A times K. Now, here, I'm using actually theorem 20. So let's take a look at this one here. And this theorem 20 is saying that, again, you have to remember we're using A and K. We're not using A and B. So we had this statement that 1 was less than or equal to K. So we're actually using 1 in K. And the C in theorem 20 is the A. All right. So here we are basically had the situation where 1 was less than or equal to K. A is positive, so A is like the C in this theorem. So basically A times 1 will still be less than or equal to A times K. All right, so that's by theorem 20. And next up, what's going to happen? Well, what is A times K? Perfect. A times K is B. So by beautiful substitution, we have that next line of our proof. And we're done. Right? That's what we needed to show. Aren't proofs fun? Don't be scared of them. They're actually really cool. And all proofs typically will fall out by definitions in previously shown theorems, if not all. Okay, so the next theorem deals with the fact that the only divisors of 1 are 1 and -1. All right, so we're going to still be using a theorem from this stuff here. Okay, this is from Appendix A in your text. So here, let's go ahead and get started. All right, what do we start with? Very good. The word proof. So, what do we know? We know that what are the ways we can get a product of 1? By using integers. Good. 1 is equal to 1 times 1, and 1 is also equal to -1 times -1. So, what can we say about 1 and -1? Good, that they are divisors of 1. Okay, well, this is something that we use a lot of times in linear proofs. Like, we suppose that there's this number from your set that you're dealing with, or this entity or quantity from a set you're dealing with, and we assume, hey, let's say there's this letter out there, call it M, and M divides 1, right? Then what we end up showing is that M is going to have to be 1 or -1, all right? So let's do it. We're going to build our stuff. M belong to the integers, and such that, remember that means such that, M divides 1. So we're supposing that M is an integer that divides 1. So, if that's the case, there's got to exist some k that belongs also to the integers such that 1 is equal to M times k. Thus, M and k are both positive or both negative. And this is again that theorem 25. All right. So we've got some cases here, right? So if M and K are both positive, M has to be less than or equal to 1. This is from the theorem we just proved, right? If you've got two positive integers, right, and the first one divides the second, then that means that the first one has to be less than or equal to the second. So that is by theorem 4.3.1. Thus, M would have to equal to what? Beautiful. M would have to equal to 1, since there does not exist a positive integer which is less than 1. So we've shown the case where they're both positive. Now, if M and K are both negative. Then what we're going to have is that negative m times negative k has to equal to m times k, and that in turn is equal to 1. Thus, negative m is a positive integer divisor of 1. So negative m would have to equal to 1, and that means that m is equal to negative 1. So what have we found? Therefore, m is 1 or m is negative 1. And we're done. Pretty cool, huh? All right. So, another theorem. And, you know, these are all in your book as well, but I just wanted to go through some of them with you. There's one that we're going to kind of hold off on a little bit. Actually, 2 of them, but they are in your book, and so I didn't want to spend your time going over them at length. The kinds of proofs that we're seeing here with me working them out are the kinds that you could see on an exam. All right. So for all integers a, b, and c, if a divides b and b divides c, then a divides c. All right. So what do we start with? Beautiful. Proof. And we got to set up our tools. So suppose a, b, and c belong to the set of integers, so they can be any integers, okay? Such that a divides b and b divides c. So we're just kind of restating our premise here, right? But from this, you know, the definition of divisibility, what must exist? There has to exist integers. Well, I'll write out the word. In this case, there exist integers. I'm just going to call them k and l, such that b is equal to a times k. That's from a dividing b. And what else would I say next? Beautiful. C would equal to b times l. And that's by definition of divisibility. Now, let's see what we've got going on. C is equal to b times l. All right, but what is b? Perfect. B is equal to a times k, and then we still have this times l. And that is by substitution. All right. And you have to be careful because you're substituting indirectly for b, so those parentheses are important. All right. What do we know about the set of integers? The set of integers are associative, right? So, or is associative. So I can write C as A times K times L. And that's because the set of integers is associative. under multiplication. All right, well, let's see what we have. What else do we know about the set of integers? We know that k times L is an integer. Since the set of integers is closed under multiplication. What else do we know? We know that A is going to divide A times some integer, right? Because A divides itself. So what can we conclude? Therefore, awesome, A divides C. Groovy? All right. Theorem 4.3.4, right? So any integer n greater than 1 is divisible by a prime number. And you've used this a lot. When you have factored things into primes, you use it all the time, right? This is one of the proofs that's in your text. It's a good proof. It's a little longer than what I would want you to do on an exam at this point. So I'm going to let you go over that, at your leisure. This next one is a theorem that we will be proving later on. We'll be proving it. It's outlined in, I think, Chapter 5 and Chapter 8. So this is important. It's the fundamental theorem of algebra. So you can figure that's pretty important. It's also called unique factorization of integers theorem. So given any integer n greater than 1, there exists, a positive integer k, distinct prime numbers p1, p2 down to pk, and positive integers e1, e2 down to ek, such that n equals p1 raised to the e1, p2 raised to the e2 times, all these are products, pk, e raised to the e sub k. And any other expression for n as a product of prime numbers is identical to this, except perhaps for the order in which the factors are written. All right. So again, we will look at this proof as we gain more skills and come back to it. But let's utilize this proof. So one way we could look at this is how many zeros are at the end of 35 to the 5th times 72 to the 6th? What do you think? Just take a moment, pause the movie if you need to, and think about it. What number, when we multiply by that number, results in a 0 at the end of our number? Awesome, 10, right? And what two primes have a product of 10? Perfect. 2 times 5 is 10. So here we go. We're going to be using some properties of exponents here, right? So specifically, we'll be using, in some order, we'll be using a to the m times a to the n is equal to a to the m plus n. And we'll be using a to the m raised to the n is equal to a to the m times n. All right? So, or will we be using that one? Yeah, we'll be using that one. And sorry, one more. We're going to be using a times b to the m is equal to a to the m times b to the m. Okay, so those are part of what we'll need for our evil plan. And let's check it out. So here we go. 35 to the 5th times 72 to the 6th. So the prime factorization of 35 is what? I mean, this is going to equal to the quantity 5 times 7 raised to the 5th. So I'm replacing the 35 with 5 times 7. And what about 72? I mean, 8 times 9 is 72. 8 is 2 cubed, right? And 9 is 3 squared. So this would be 2 cubed times 3 squared, all of that raised to the 6th power. So I'm replacing the 72 with its prime factorization here. But remember, our whole evil plan was we want to get the 2's and the 5's together, those factors. So let's go ahead and use the, what is it going to be, the third line, right, to write this without grouping symbols. So we're going to have 5 to the 5th times 7 to the 5th times 2 to the 3 times 6, and then times 3 to the 2 times 6, which in turn is 5 to the 5th times 7 to the 5th times 2 to the 18th times 3 to the 12th. Cool so far? Great. So let's go ahead and get the 2's and the 5's together. And so we'll have 2 to the 18th times 5 to the 5th. And then we'll have times 3 to the 12th times 7 to the 5th. Okay. I can only use, this third property, right? If I have 2 to the 5th times 5 to the 5th. So I'm going to be using this first one to rewrite the factors of 2 as 2 to the 5th, and then times 5 to the 5th. I'm going to write the remaining factors of 2, and I'm going to need 13 of them, because when you multiply the same base, you add the exponents. So 2 to the 5th times 2 to the 13th is equal to 2 to the 18th. And then we have times 3 to the 12th times 7 to the 5th. And so this is what happened to the 2's. So 2 to the 18th is broken down to 2 to the 15th times 2 to the 13th. Cool, cool? All right, so continuing, we can now write this as 2 times 5, all raised to the 5th, right, times 2 to the 13th times 3 to the 12th times 7 to the 5th. And that in turn will give us 10 to the 5th times 2 to the 13th times 3 to the 12th times 7 to the 5th. So 10 to the 5th means that we're going to have how many zeros? It implies that there will be 5 zeros are at the end. Of 35 to the 5th times 72 to the 6th. All right, pretty cool, huh? One application. Okay, so now let's get into some proof stuff. First of all, we want to figure out, hey, are these statements true or false, right? If they're false, then we would have to provide a counterexample. And if they're true, we need to prove them, all right? So the product of any two integers is a multiple of 4. Okay. Well, let's think about it. Pick any two even integers. 8 and, I don't know, -4. So 8 times -4 is -32. And isn't -32 even? It can be written as 2 times -16. Okay. We can try 2 more. How about 10 times 4? That's 40. Can be written as 2 times 20. So I think it's true. Those 2 specific examples don't prove it, right? But I can write these things in general, and then I can show that they're true. So start off with proof, right? Now, you got to name your integers, right? So why don't we name them M and N? And what kind of integers do we want them to be? Any even integers. Well, what's even mean in math? Good. You can double some integer and you get that even integer. So there has to exist some other 2 integers, call them k and j, such that m is 2k and n is 2j. That's by definition of even, right? Okay, so let's see what that leaves us with. I need to multiply them, right? So the kind of evil plan here, right? So if we think of our evil plan, multiple of 4, what does that mean? Means that we need to show what? We need to show that m times n equals 4 times some integer. Right? Okay, so that's where we need to go with this. And it's fine for you to write this on an exam. Just have it to the side, right? So I don't think you're trying to assuming what you're trying to prove. So with this in mind, right? Okay. Well, m times n, well, what does that equal to? Perfect. 2 times k times 2 times j. Good so far? And that's by what? Substitution. All right. Well, I'm not quite there yet, okay? This one will also equal to what? If I commute the 2 and the k, do you see I'll have 2 times 2 times k times j? And I can do that because the set of integers is commutative under multiplication. All right, well, this in turn is 4 times k times j. Good so far? All righty. What do we need to say now about that product k times j? K times j belongs to the set of integers. Why? Since the set of integers is closed under multiplication. When you multiply 2 integers, you get another integer. And so now, do you see we've done it? We've completed our proof. We can now do our grand conclusion. Therefore, the product of any two even numbers, actually, we're going to say integers, is a multiple of 4. Groovy? All right. What about this next one? The sum of any 3 consecutive integers is divisible by 3. What does consecutive mean? One right after the other, right? So 1, 2, 3 are consecutive integers. 3, 4, 5, negative 3, negative 2, negative 1, right? 0, 1, 2. So, okay. What are we really doing here? We're taking some initial integer. To get the first consecutive integer, you would do what? Beautiful. You would add 1 to that integer. What about the next one? Awesome. You'd add 2 to the same integer, right? Or you could add 1 to the one before. So let's think about, do you think this is going to be true? All right, well, 2, 3, and 4 are consecutive. Their sum, 2 plus 3 plus 4 is 9, and 3 divides 9. Try again, right? How about negative 3, negative 2, and negative 1? So you'd get negative 3 plus negative 2 is negative 5, plus negative 1 is negative 6, and 3 divides negative 6. So I think it's true, right? So since I think it's true, I need to do this in general. So I need an integer. So let n belong to the integers. It can be any integer, all right? So n plus 1, and n plus 2 are consecutive integers. We know they're integers because why? Good. The integers are closed under addition. Alrighty. Well, now what? Well, why don't we add them together? See what we get. N plus 1 plus n plus 2 is what we're adding. So when I simplify that, right, and use algebra to simplify, what do I get? Beautiful. I get 3n plus 3. And what can I do? I can use that distributive property, right? To write this as 3 times n plus 1. And that I can do because the set of integers is distributive. All right, well, what do I need to show now? I need to show that n plus 1, or I need to state that n plus 1 is an integer. I'm just going to write closure. So 3 divides 3 times n plus 1 by definition. Sorry. Therefore, the sum of any 3 consecutive integers is divisible by 3. And we're done. Awesome. Okay. What do you think about this next one? For all integers a and b, if a divides b, then a squared divides b squared. All right, well, let's think about this. How about if a is 5 and b is 10? So a squared would be 25, and then b squared would be 100. Well, 25 divides 100. Let's try, we know the evens I think should work, but let's try it. What if a is 6 and b is 36? Or let's do b 12 since I'm doing this in my head. Right, so 6 squared is 36. 12 squared is 144, right? So 144 is indeed divisible by 36. So I think it's true. So let's check it out. Let a and b belong to the set of integers such that a divides b. Well, since a divides b, what's the setup? Perfect. There exists some k. And what does k belong to? The integers. Perfect. And it's going to have to make b be equal to a times k. Groovy? All right. So b equals a times k. Well, if you square them, what will we have? B squared would equal to A times K, the quantity squared. And by properties of integers, that would be B squared is equal to A squared times K squared. Well, for B squared to be a multiple of A squared, we'd have to write B squared as A squared times some integer, right? So K squared belongs to the set of integers by what? Perfect closure properties. So A squared divides, A squared times K squared, by definition, of divisibility. Hence, A squared divides B squared. Awesome. All right. So now, last example for this section, I think. Yep. Let's apply this. In a certain town, 2/3 of the adult men are married to 3/5 of the adult women. Assume that all marriages are monogamous and that there are at least 100 adult men in the town. What is the least possible number of adult men in the town? How about adult women? So let's check it out. Let's get a foundation here. Why don't we let M denote the number of adult men in the town, and let W denote the number of adult women in the town. All right, well, what do we know? We know that we know that 2/3 of all the men, right? 2/3 of all the men So how can I represent that quantity? 2/3 of all the adult men can be represented as 2/3 M. Okay. And remember, monogamous means they're married to just one person, right? Not multiple wives or multiple husbands. So we could set that equal to what? Good. 3/5 of the adult women, right? So 3/5 of the adult women means 3/5 of W. Cool so far? Awesome. Okay. So what else do we know? All right. We know that M has to be greater than or equal to 100, right? And working with this equation that we've made, do you see this is equivalent to, if I clear out the denominators, right? So what, times 15 So if I clear out the denominators, what would happen? I would have 10m is equal to 9 times w. So what needs to be true? I mean, we don't know how many women there are, right? And so for this to work out where we have a whole husband and a whole wife, what needs to be true divisibility wise? I mean, doesn't 9 need to divide 10 times m? Okay, well, we know 9 doesn't divide 10. So what would that mean? That would mean that m has to be a multiple of what? Good, 9. Well, the fundamental theorem of algebra says what? It says that 9, therefore, would have to divide m. So fulfilling those two requirements gives us m has to equal to 108. There must be 108 men. Well, coming back to our equation here, right? And applying it over here, we could say that W, if we isolated W, would be equal to 10/9 times m, right? So W would equal to 10/9 times 108. And that would give us 120. All right, so writing it out nicely, we would say what? The least possible number of adult men and women in the town is 108 and 120 respectively. Cool, cool. All right, well, that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you are watching the show. And if you like what I'm doing, please subscribe. Thank you. Have a wonderful day. Bye.